Let's take a minute to talk about the filling, or rather, also the emptying order for cations. For neutral ions and negatively charged atoms, electrons are added to the orbitals in order of increasing energy, as according to the Aufbau principle. Before we get started, let's remember that cations, especially those coming from D and F block elements, are funky. When a neutral atom loses electrons to become a cation, its core electron configuration, or the electrons that are contained within the noble gas configuration of the previous row, stay the same. However, when electrons are lost from the valence or outer electrons, those not contained in the noble gas configuration, they will be rearranged by order of increasing n level. Practically speaking, this means that metals lose their electrons in the higher n level s orbital rather than the seemingly higher energy d orbitals that have lower values for n. Remember, when an atom gains or loses electrons, it's in an attempt to achieve noble gas configuration. In order for cerium, which is our example element, to achieve that configuration, it would want to lose electrons until it had the electron configuration of xenon. So this will govern the ionization patterns of cerium. Now, you may be wondering, why do we remove electrons from the outermost level in? And why do we rearrange electrons, the valence electrons, in order of increasing n? There are two key factors. The first one is degeneracy. Remember that as we increase in n and get further from the nucleus, those energy levels are getting closer together. We can see that on this graph where we graph the empty orbitals with increasing energy, that once we get up to those 5, 6, and 7 n levels, those orbitals are all relatively close together, which is why electrons can hop between those orbitals relatively easy. The other reason is our good old friend Zeffective. Remember that 6s, 5d, and 4f orbitals all have different numbers of protons. But since they're in different n levels, they also have a different number of core electrons, which will affect their Zeffective. Once these orbitals accept electrons, the Zeffective experienced by the electrons and the different orbitals decreases as we go down a group. Therefore, electrons that are held in higher levels of n are held less tightly by the nucleus and therefore are more likely to be surrendered than electrons with a lower level of n. So let's go back to cerium. Which electrons will be removed first? To do this, we have to think about the filling convention for cations from the opposite perspective. Whereas we fill valence electrons from lowest n to highest n, we remove them from highest n to lowest n. Because 6s electrons have the highest n level, they are the most shielded from the nucleus and experience the smallest charge-charge attraction. Therefore, they are the easiest removed and the first to go. Once we have lost electrons, the filling order applies to how we would reorganize the valence electrons into a new cationic configuration. If we were to follow neutral atom convention, like we did in class, we would get an electron configuration of xenon 6s0, 5d1, 4f1. However, what we missed in class was that the electron filling convention that we talked about, so the electron convention that's right here, now applies to how we would rearrange the valence electrons in a cationic atom. If we were to apply the cation filling convention here, we would rearrange the electron configuration to put both electrons in the orbital that had a lower n level. So in this case, it would be 4f. What would the next electron or electrons removed be to get the electron configuration for cerium 4+? Based off the filling pattern up here in the notes, if we were to go from the opposite direction to remove electrons rather than to fill them, You may be tempted to think that the next electron to be removed would be the 5p orbital, since 5p comes after, since 5p would be the next orbital that would have electrons in it that would come after 6s in terms of decreasing n level. However, this does not happen. Why not? Remember, when elements gain or lose electrons, they're trying to get closer to the noble gas configuration. For cerium, that's to achieve the configuration of xenon. If cerium were to take an electron out of 5p, it would lose its noble gas configuration. That is not energetically favorable. What the order means is that when we remove valence or outer electrons, but without tapping into the core electrons, we remove them in order of decreasing n level. But that's only for the valence or outer electrons, not the core electrons. So let's look back at our cation filling or emptying order. The 5s and 5p are not available to us because they are contained within the core electrons of the noble gas configuration for xenon. So we would have to go to the next n level where we hit 4f, which happens to be where our electrons are hanging out anyway, our valence electrons. If we have 2 electrons in the f orbital, these will be the electrons that will be removed to make cerium 4+. So we can write its configuration as Xe but you'll also see this written as krypton 5s2 4d10 5p6. The second way of writing this electron configuration indicates that after removing the original outer electrons in the 6s, 5d, and 4f subshells, the new outer electrons are in the 5s, 4d, and 5p orbitals. So if you remember anything from this video, it should be that atoms become cations by removing valence electrons in order of the highest n level to the lowest n level. We rearrange valence or outer electrons in order of increasing n level, so the lowest n first, after removing electrons. And then finally, when removing electrons, we do not tap into the core noble gas electron configuration.